Okay, we're now on version 4 or track 4 of this chapter 7 lecture on video. Anyways, now that we've got all this experimental evidence, let's kind of summarize it in what I showed you in class was called the electron manifesto, something I made up a long time ago. And this is what an electron might say to you if it was telling you all about itself in as clear and concise a way as it can. Maybe it's the CV for an electron or something like that. But the key thing is an electron exists in an orbital. And what an orbital is, and this is important, it's a region of space of a certain energy. That's the key point. That can house 2 and only 2 electrons. Now, only 2 electrons can be in there. They come in many different shapes and sizes. It doesn't matter how big or small they are. Only 2 electrons can go in there. And they don't have to have 2. They can have 1 or they can have 0. Something you should realize right now is that an orbital is a made-up thing by human beings and they don't really exist. Therefore, they're just there to help us. They're a tool for us to use, and they work very well in that way. There's a lot of things in science that are just tools that we use that don't really exist. Secondly, the electron would say, hey, if you want to describe me, if you want to find me, you're going to need to use my 4 quantum numbers. Now, your quantum numbers are not too different than, let's say, your address, which tells you what street you're on, what house you're on in that street, what city you're in, and what state you're at. Okay, that's essentially what we're doing here. First off, there's the principal quantum number n, which we've all had experience with. It really is telling us it's mainly telling us the overall energy of the electron. Though there's an angular momentum quantum number right here, which also does play a role in the energy. But for us, we're going to think about this as telling us the shape of the orbital. Shape of the orbital, and the energy of the orbital will be right here, the energy of the orbital. The azimuthal quantum number, m sub L, will tell us how many of any shape. And then finally, the electron spin. It can either spin up or down, which in mathematical terms is a plus 1/2 or a minus 1/2. Don't worry about why it's a plus and minus 1/2. That is something for nuclear physics. We won't get to it ever. Great. So when an electron is excited, if you were to heat it, hit it with a photon, bang it with a hammer, whatever, it can jump to another orbital if there's room in that orbital, and if you give me the exact amount of energy for that jump. We've already talked about this. You can't give any more or any less. It's got to be the exact amount to get it where it needs to go. And if that electron is excited, it will always try to go to the lowest energy orbital available by giving away some energy. That means it's going to emit. So this is absorption, and this is emission. Things we've already talked about. It's normally going to give this away as light, though there are ways for it to give some of its energy away as heat, and that is a whole different story in a whole different course, not this one. For now, everything will be light. Let's talk about these quantum numbers one more time because they define where that electron is in the atom, and there's a thing called the Pauli exclusion principle, which states that no 2 atoms can have the same 4 quantum numbers. Okay, so that means no 2 electrons in a particular atom. If we have Bob the atom over here and Steve the atom over there to the right, then those 2 atoms can have electrons with the same 4 quantum numbers because they're not in the same atom. All right. Cool thing is that I just told you a little bit about these. Principal quantum number gives you the energy, and it goes from n equals 1, 2, 3 all the way up to infinity. All right. The angular momentum quantum number can be found anytime you want by, if you know what n is, it starts at 0 and it goes up in steps of 1 all the way up to n minus 1. All right. The magnetic quantum number starts at minus L and then goes to all the way up to positive L, once again in integer steps where we just keep adding keep adding 1 to it. So if L was equal to 2, then m sub L would range from minus 2, minus 1, 0, plus 1, and plus 2. And then finally, we have the spin quantum number, which I've already told you about. Okay, and we'll be back in a second to talk more about these quantum numbers here and about these terms S, P, and D that we introduced before.